background concepts that we had to remember. Now we're going to move on to some key quantities to study turbulence. So this class is going to focus on shear and strain and what processes drive shear and strain in the ocean. So the outline of this is going to be first, we're going to talk about what is shear, talk a little bit about the difference between vertical and lateral shear, why vertical shear is important, and some examples of vertical shear instabilities. Then we're going to talk about strain and actually talk about the two definitions of strain. The first one, strain rate, and the second one, strain variance. And then we're going to finish up with some of the processes that increase vertical shear in the ocean. So, shear is inherent in the three-dimensional eddy motion of turbulence, and it is defined as the velocity spatial gradient in a direction normal to the flow direction. So we can define, for example, lateral shear, the meridional derivative of zonal velocities, or the zonal derivative of meridional velocities, and vertical shear, which is just the change in depth of the zonal and meridional velocities. And typically in the ocean, the velocities typically vary over smaller vertical scales and larger horizontal scales. So we end up with horizontal shear that's typically way smaller than vertical shear. So for example, thinking about lateral shear, some of the processes that drive it are, for example, mesoscale eddies or an ocean front. And in a mesoscale eddy or a front, we typically have the velocity varying over 0.1 to 1 meter per second, but it varies over a lateral scale that ranges from 10 to hundreds of kilometers. And we end up with a lateral shear of order 10 to the minus 6, 10 to the minus 5 seconds, seconds to the minus 1. But for vertical shear, on the other hand, these are some plots, time series from a wire walker. The x-axis is time and the vertical axis is depth. And here, the first panel, we're showing zonal velocities, and the second panel, the meridional velocities. This is in the tropical Pacific, so this is showing the equatorial undercurrent. And what we can see is that the currents still vary over 0.1 to order 1 meters per second, but now they vary on a vertical scale of the order of 10 to hundreds of meters. So you end up with vertical shear that's way higher than horizontal shear, order 10 to the minus 4 to 10 to the minus 2 seconds to the minus 1. And so in turbulence, vertical shear is going to be more important than horizontal shear. And there are two main reasons why vertical shear is important. The first one is that vertical shear is important to steer tracers around. As Justin was saying, steering produces and intensifies tracer vertical gradients. And when these vertical gradients are intensified, you end up with a bigger interfacial area between different fluids, and that's going to favor mixing through molecular diffusion. And so this is an example of a zonal flow that has a positive vertical shear. And if we think about an initial blob of tracers distributed as this square here, over time, these tracers are going to be stretched out in this direction. And the shear is going to have this effect of increasing the interfacial area. So that's the first reason why vertical shear is important for turbulence. The second one is because vertical shear can trigger turbulence itself. And by triggering turbulence, we're going to shift from those molecular diffusivities that Justin was talking about to turbulent or eddy diffusivities, which are way stronger, way more effective for mixing. And we're going to end up with the vertical diffusion terms in the equations being more important. And what I mean by that is that, for example, in the x momentum equation, we have the local variations in the zonal velocity. We have the advective term, Coriolis pressure gradient, and then the diffusion term. When vertical shear triggers turbulence, this term, the viscosity is going to increase, and this term is going to become more important in our equations. Then for tracer conservation equation, similar example, we have the rate of change of tracer C. It changes because of advection and vertical diffusion, and turbulence is going to increase. the kappa, the diffusivity, and this term is going to become more important. So those are the two main reasons why vertical shear is so important in turbulence. And some examples of what kind of instabilities are triggered by vertical shear. A classical one is the Kelvin-Helmholtz instability that Ankita is going to give more details to us tomorrow. But here I just wanted to show a video of this instability happening. Let me just increase the quality. So this is a lab experiment where you at the bottom we have dense water dyed with blue, and at the top we have lighter waters with no dye. And what she's gonna do is that she's gonna tilt this rectangular tube. The dense water is gonna flow that direction because it wants to be at the bottom, and the light water is gonna flow this direction because it wanna stay on top. And so by tilting the tube, there's gonna be a vertical shear happening, and that shear is gonna generate overturns. And so let's see that happening.
Here we go, bro. Here we go. Okay. Please work. Please work. Oh no! Yeah. Oh, is that not doing a lot? You know.
So yeah, these are the Kelvin-Helmholtz instability. Right here, we're gonna see these overturns are what we call the Kelvin-Helmholtz billows, the overturns that are gonna form here. And you can see that rapidly, once they're formed, all the steering favors mixing, and the waters mix way faster than if you were to leave the tube there, just with molecular diffusion acting. Here's another cool video just to give a zooming of the beautiful overturns. So the same thing, the tube is going to be tilted. There's going to be vertical shear. And we see the Kelvin-Helmholtz billows forming and generating a lot of mixing between the two water masses. And so this instability, we can see them in nature. Sometimes when we look in the atmosphere, we can see these Kelvin-Helmholtz billows in clouds, which is pretty cool. And but this is a process that's really small scale, and it's really hard to model it. So to get this kind of processes, you usually need some LES modeling. And here is just one example of this. And so here on the left, we have the different water masses, and this on the right is the zooming into this square here. We can see that there are lots of overturns, and inside the overturns, there are other overturns. There's a cascade of smaller eddies coming, smaller eddies down to the grid scale. So it's a really small scale process. And you can really see that like all this steering creates a lot of surface interfacial area that molecular diffusion can act on. Yeah, I could stare at this the whole day. It's really pretty.
Thank you. Can you say more about what makes an LES different from other GCMs?
Yes, so the GCMs, you have to discretize your equations to different little boxes. And in a GCM, you kind of like stop maybe with a horizontal resolution of maybe 1 kilometer. That's for like a really high resolution GCM, and a vertical resolution of meters or tens of meters. But these processes, they happen on the scales of like centimeters or meters. So all of these processes in a GCM, they're parameterized by one simple equation, and they're not really represented. So on an LES, you resolve these processes on a shorter domain, but you can really go to this fine scale and you directly solve them other than just parameterizing. And so here's just two snapshots from the video. The initial time when there was no deformation, there was no mixing. And future time after turbulence happened, there's a lot of deformation. You see all this steering happening. And this deformation, we can quantify how much is going to be deformed or how much was deformed with the strain parameter. And so all the stretching and thinning of these fluid parcels, they're generated by the shear that I already talked about, but also by local divergences and convergences on the fluid. This is a sketch in a schematic representing how a checkerboard pattern will be deformed by this flow here, which a horizontal flow which has both shear, you have variation of the velocities in space, and you also have places with convergences and divergences. And the strain is going to stretch these particles. And the way that we define strain rate mathematically is with the strain rate tensor. So Sij, which is the strain rate tensor, is half of del ui del xj plus del uj del xi, where I and j are the if and jf components of u and x. And so this tensor, we can divide it into two different components. The first one is the normal strain rate, which is basically the component because of convergences and divergences. And these components are SXX, SYY, SZZ. And so if we plug the XX there, SXX is just going to be half of del UX plus del UX. So SXX is del UX. And similarly to the other components. And then we have the other component of the strain rate tensor, which is the shear strain. And that's the changes of the fluid shapes because of the flow shear. So SXZ, SYZ, SXI. So SXZ, for example, it's going to be W del Z. And then the total absolute value of the strain rate is going to be the square root of this SXX squared, SYY squared, all of these terms together. So this is what we use to compute how much strain the flow field is going to have. Now, this is not the only definition of strain. It's really useful, but another definition of strain that's often used in turbulence is the strain variance. So we can look at a picture like this, and we can kind of tell where are the places where there's more deformations, like around here, around there. And so the strain variance kind of aims to get that kind of information by measuring the change in stratification through the water column, and just quantifies how much the deformation varies across the fluid. So if we were, for example, to take a vertical a profile through this, the strain variance will look like something like you have very constant stratification, and then suddenly you have a bunch of wiggles, and then it's constant again, you have more wiggles here. And so with this measure, we can kind of get a sense of how much turbulence happened in that place. And mathematical definition, if any of you guys are interested in computing strain variance, this is what Whalen and colleagues used in 2015. So the strain variance zeta z is defined by n squared minus n squared phi. N squared is the stratification, which is defined as minus g del rho del z over rho naught, where g is gravity, rho is density, rho naught is the reference density. And in this case, the n squared fit is a quadratic fit that just aims to smooth the n squared profile. So basically the upper part of the equation, n squared minus n squared fit, is trying to get just the wiggles, just separate the wiggles from the total profile. And then the n squared bar is just an average of the n squared fit. So this is the strain, and then the strain variance is defined this equation here, which where SSTR is the Fourier transform of the strain, and Kz is the vertical wave number. So the strain variance is you get the strain variance by computing spectra of the strain different segments along a profile. And so, okay, this is a really crazy equation, funny, fun, but why do we use this? So as I said, sometimes you go to the ocean, you don't have direct turbulence measurements, but you can get density profiles, and then in the absence of these turbulence measurements, you can use those fluctuations on the density profile to estimate turbulence through parameterizations. So parameterization that's very famous is the fine scale parameterization. Jen's gonna tell us about this next week, and then Kita too. Next week, no, week 3. And this parameterization basically uses the density fluctuation information combined with some theory of internal waves, of breaking internal waves, and then you can get an estimate of how much turbulence is happening in the water. And this is really useful. It has allowed us to get estimates of global patterns of turbulence in the ocean. This is a plot of the log of kinetic energy dissipation rate, which we're still going to talk about this week. But basically, just from Argol profiles around the globe, you get the density fluctuations and you can get an estimate of epsilon, which is pretty cool. Now, so now we know what is shear, what is strain. Let's talk about what processes in the ocean can increase shear or strain variability. So let's make a table here, and one side we're gonna have shear, the other side we're gonna have strain. And a lot of these processes that drive high shear and turbulence are gonna also drive strain variance, but there are some processes that generate strain variance that are not related to shear-driven turbulence. So do you guys have any, can you guys tell me some processes you think increase shear in the ocean? Flow over bathymetry. So I'm gonna write that as bottom boundary layer processes.
Surface stresses, like stresses.
Surface stress. And I'm also gonna write here wind-driven currents.
Gradients,
Gradients.
like gradients in density or.
Gradients in density.
Well, I get it from. Yeah, exactly.
Okay. From
Okay. Yeah.
any more thoughts? So a big one is internal waves. When internal waves break, they generate a lot of shear. So that's going to be an important one. And one more is, I don't know if you guys ever heard, but some mesoscale instabilities, they also increase shear.
Upwellings?
Sorry?
Upwellings?
Upwelling. Yeah, you can have the overturning cells and have more shear. Okay, so all of these can generate shear and increase turbulence. The fronts can be like related to some mesoscale instabilities, upwelling and secondary cells also. All of these can generate shear-driven turbulence, and they're gonna drive strain variance. Can you guys tell me any processes that drive strain variance but are not related to shear-driven turbulence? Anything that can generate wiggles in the stratification, but not really because of shear-driven turbulence. Yeah, that's a harder one, but
Topography, imagery still.
water over
But
bathymetry.
imagery, like topography, can still, doesn't have to be.
Yeah, so it can be related to topography. So one of them is like water mass intrusions that can happen because of upwelling or subduction along a front. So just gonna write water mass. And then another one is double diffusion, which I don't know if you guys ever heard of, but we're gonna learn about that this week. Just gonna put it here.
There's something in the chat as well, frontogenesis.
Frontogenesis, nice. Yeah, frontogenesis can be related to the mesoscale stuff. Thanks, Kelly. Yeah. So point here, there are a bunch of ocean processes that drive all of these that drive more shear and more strain. And then going back to the idea of using strain variance to estimate turbulence, we really need to keep in mind that there are some processes here that are not really related to shear-driven turbulence. So this would be problematic for some of the parameterizations, but we can talk more about that later. So we're gonna talk about tomorrow in the lecture with Ankita. We're gonna talk a little bit about some mesoscale instabilities. Tomorrow in the practice of examples of turbulence in the ocean, we're gonna talk about wind-driven currents, more specifically diurnal warm layers. Today, I just wanna give you guys a review or an introduction to internal waves, which are a big process that drives shear in the ocean. So internal waves, because the ocean is stratified, it supports the existence of internal waves. This is a time series. X-axis is time, the y-axis is depth, and we can see all these, and the colors are temperature, the lines are density, and we can see that there are a bunch of fluctuations. There are big, there are longer time scale fluctuations, and there are smaller wiggles. These are all internal waves that happen in the ocean because there's stratification. And a way to get a mathematical expression, we can find a way to get a mathematical expression that expresses all the physics of internal waves by going back to the Navier-Stokes equations that Chastain reviewed in the first class. And by doing a couple assumptions and combining the equations, we can get to this thing called the dispersion relationship. So the assumptions that we're gonna make, first we're gonna neglect viscosity. We're gonna assume that there is small amplitude, basically neglecting nonlinear terms. For this example, we're gonna assume constant stratification, and then all the Navier-Stokes equations that we saw, they're gonna simplify to these guys. And I'm not gonna go over the whole thing to get to the dispersion relationship, but there's a way to combine these equations, and after that, if we assume a plane wave solution, basically, if we assume that there are perturbations that have W, for example, is expressed by an amplitude plus an oscillatory solution that depends on X, Y, Z, and time, we can find this thing called the dispersion relationship. This is the idea of the wave. Here we have omega is the frequency, F is the inertial frequency or the Coriolis frequency, M is the vertical wave number, N squared stratification, KH is the horizontal wave number, and K vector is the whole wave number vector. And so this relationship embodies all the physics of internal waves. It tells us a lot. And an analogy that I like to make is that this is kind of like the eDNA of the wave. So if you go out to the ocean and you find a way to measure all these parameters, there's only one frequency that's going to correspond to that combination of parameters. It's kind of like if you go to the ocean, you find a tiny piece of eDNA that can only be sea line. For us, it's going to be a near inertial wave. I don't know. And then if you go out and measure other parameters, there's this eDNA that kind of looks like the other one, but is actually nudibranch, or that's an internal type. So that's how I like to think about the dispersion relationship. And then there are a bunch of other properties that you can get from the dispersion relationship. first one, we can further simplify this dispersion relationship to this equation, where now we're gonna have, instead of having all the wave numbers, we're gonna have the dispersion relationship vary in terms of this angle theta, which is basically the angle of the wave number with the horizontal plane. And then our internal waves, they're gonna depend only on stratification, inertial frequency, and the angle of the wave number vector. With those three things, you can find the frequency of the internal waves. And this relationship also give us the range of existence of internal waves. They can only exist between F and N, between the inertial frequency and the buoyancy frequency. And this is like 95% true. This is like the simple scenario where we didn't consider a background flow. But if we have internal waves propagating over a background flow with vorticity and baroclinicity, then then the vorticity and the buoyancy gradients, the lateral buoyancy gradients, they're also going to affect the frequency and the range of existence of the internal waves. And they're actually going to make this minimum frequency shift a little bit. Okay.
Wait, sorry, I had a question. What is M?
N?
M.
M. Oh, sorry. M is the vertical wave number of the wave.
Oh, okay.
Yeah. Okay. And so other properties from the internal waves that we can get from the dispersion relationship, we can find the phase speed, which is omega divided by k, and the group velocity, which is del omega del k. And omega by k tells us the velocity of which of like the phase of the wave propagating, whereas the group velocity tells us the velocity of the wave packet propagating, the energy propagating. And waves are really weird. Here is an example, a video showing two different waves. There is the red wave, which has a higher phase speed. The red dot tracks the speed of that phase propagating. The blue wave tracks the velocity of the other wave propagating. And then if you sum both waves, you have this wave packet. And you can see that the wave packet is actually propagating a different direction. Now, like the pink dot shows the group velocity, whereas the green dot shows the phase velocity. And so waves are really funky. You can have this crazy situation of phase going one way, energy going the other direction. And internal waves are no different than that, but even crazier. For internal waves, an important property is that phase speed propagate perpendicular to the group velocity. And in this video, if we track the red phase here, you can see that the phase is propagating up, while the whole wave packet is propagating down. The group is going down. So this is another important property. If we get a time series and we see the phase of the wave propagating up, we know that the energy of the wave is going down. Okay, so what are the most important or the most energetic internal waves in our oceans? This is a plot of the spectra of the wave. The y-axis is the spectra, how much energy is on the waves. And on the x-axis, we have frequency. We're going to talk more about spectra throughout the week. These spectra, on this plot, they divided the waves into those that are propagating down, the solid line, and the waves that are propagating up. And we can see that there are two main peaks here. The one near F, these waves, it's what we call the near inertial waves. And another peak on the M2, the semidiurnal tide. Those are the most energetic internal waves in the ocean. And something that's interesting too is that the semidiurnal tide, we kind of have a similar peak for both downgoing and upgoing waves. But for the near inertial waves, it's really a high peak for the downgoing waves, not much from the upgoing. That's because the near inertial waves, they're formed by wind, so they always come mostly come from the surface. And okay, so we've learned something about the internal waves now, but how do they actually contribute to mixing? There are going to be several different ways of wave breaking in our oceans, and when the wave breaks, they're going to increase shear and lead to turbulence. So near inertial oscillations, for example, they can propagate down, break at some spot. You can have interactions between different waves generating breaking. You can have tidal flow. Some of those waves break locally. Some of the waves propagate remotely and break when they interact with topography. And you can also have lee waves when you have currents interacting with topography. You form these lee waves in the lee of topography, which break. So let's go over each of these waves because they're going to be important. We might see some of them when we go out to sea. First one, the near inertial waves. Near inertial waves, they're caused by wind perturbations. So the ocean has a natural frequency of oscillation. You can think of it as like when you're playing your guitar, there's a natural frequency for each string that you play. The natural frequency of the ocean is the inertial frequency. So if you perturb it, you're going to generate oscillations with that frequency. And this is a map from a famous experiment called the Ocean Storms Experiment by Tassaro. And they had a bunch of drifters, and after a storm passed by, they saw that all the drifters started oscillating similarly with the same frequency, and this is what we call the near inertial oscillations. Now, some of these water parcels they have slightly different frequencies. Let's say one of these is rotating faster, the other one's rotating a little bit differently. And these differences in the phase of the waves, it's what's gonna generate the near inertial waves. So all this dephasing can generate convergences, and these convergences pump the thermocline and radiate near inertial waves downward. You can have high mode near inertial waves. High mode is if you have the water column, you're gonna have a lot of different velocities, positive, negative, whereas low mode is more like less changes in velocity over the water column. And so the high mode ones are the ones that generate more shear, and they break sooner than the low mode ones that can propagate away for longer times. And this is an example of how we see near inertial waves in a plot. This is also a time series. X-axis is day of the year. Y-axis is mean isopycnal depth. And here the near inertial waves are the alternating bands of red and blue. We're plotting zonal shear here. And we can clearly see that the phase propagates up with time. So this is an example of an internal wave packet that's going down. We know that the phase is going up, so the energy is going down. Okay, but how do these waves actually break? So there are a bunch of, I bet there are a bunch of surfers here. A classical example is that for surface gravity waves, their phase speed, their group velocity depends on the depth of the ocean. So offshore, we have all these waves with similar properties, similar wavelength and stuff. But as they approach the coast, they're gonna find different topography, and that different topography is gonna refract the waves, which is gonna make some of the waves concentrate on headlands, where the energy is gonna be concentrated here. You're gonna have more breaking here, whereas at the beaches away from headlands, the wave energy diverge. So near inertial waves are also a type of wave that can refract because they're propagating through varying media. But for internal waves, what's gonna drive the phase speed and the group velocity is again stratification, the local inertial frequency, vorticity, and lateral buoyancy gradients. So when they're crossing a background flow with varying these properties, the waves can refract and can concentrate their energy at a specific spot where they're gonna break. This is an example of a numerical simulation. The x-axis is distance, the y-axis is depth, And on this simulation, they're trying to represent how a near inertial wave packet that's generated at the surface, how it propagates across an anticyclone. And something that happens in anticyclones is that the waves propagate down and they tend to break. They refract and they reach a region with almost zero group velocity, where the energy of the wave amplifies. You're going to have more shear, and that's what's going to trigger turbulence and braking. So this is the wave packet going down, and you can see that there's more shear where the wave breaks, and you increase the dissipation rate, another turbulence quantity. There's more braking of the wave here. This is from a numerical simulation, but these other plots come from observations that Charlotte was involved with, and I think maybe Camila was also in the cruise, TFO. So this is a warm core ring of the Gulf Stream. This is an SST map, and the velocities of the surface velocities of the ship crossing it. And here we have two vertical sections of the anticyclone, distance and depth. And we see these bands of high shear at the bottom of the anticyclone. These are the near inertial waves that travel down and got trapped in those critical layers, the regions with near zero group velocity. And when we look at the research zone number, we're also going to learn about it tomorrow. When you have low research zone number or high inverse of research zone number, means that you have the potential for shear-driven turbulence. So these are really cool observations of like this process happening in the real ocean. Okay, now let's move on to internal tides. Internal tides are the other really energetic internal waves in the ocean. The internal tides are born when the barotropic tide flows above topography. And in this graph, this is an example of internal tide being generated when it crosses a ridge. And so all these crazy beams here, these are the internal tides being generated as it's interacting with topography. And I'm gonna show a video here. Yeah, okay, it's in loop. So let's start again. So you start with the barotropic tide flowing above this topography. You have a lot of beams being generated. These are the internal tides. And then a lot of this energy close to the seamount, it has higher shear. These are the high mode internal waves. These get dissipated locally, generate a lot of turbulence. But some, and then the remaining energy, which is like the low mode waves, just a couple changes in velocity with that, they can propagate really far away and generate turbulence elsewhere. This is an example of internal tides from, should have done this before. These are examples of the internal tide signal taken from satellite altimetry. You can find the signal at the surface of the bumps of the internal tide. So these are internal tides generated in the Hawaiian chain when the barotropic tide interacts with it. Part of it goes north, part of it goes south, and there's also this component here that comes out of the Aleutian Islands. So these are pretty cool, also real observations of internal tides. And then again, part of these waves, the high mode internal tides get dissipated locally, but the low mode waves, they can propagate offshore and they can propagate away, and they're going to interact with the shelf break in different regions where they can generate more turbulence. Next, I want to show a video of this simulation of these waves generating turbulence. Okay, so here we have the internal tide interacting with a sloping bottom, and what we can see is that there's a phase where the velocities are upslope, and you again, That velocity is going upslope and you form a lot of pores. And then when it shifts, it generates these overturns that create a lot of turbulence. Overturns, upslope, change phase, and you have overturns. So this is also turbulence generated because of the shear of the varying internal tide.
Can you see in that figure a bore, like a destructor?
Yeah, the bore is like in the upslope case. So here, the bore is like when the density
Propagate along the bathymetry,
along the bathymetry.
but those one propagate in the same isobat, or in this case is along
Across isobat.
Okay.
Yeah. So bores are like when you have the bottom, not always attached to the bottom, but when your density, you have an isopycnal kind of like this, there's a pycnal really vertical and it propagates up. There's a lot of turbulence associated with this too. So the bar propagates up, and then when the flow reverses sign, you're gonna have this overturn that's represented in the video. So this is just showing the temperature and the isopycnals, but there's this other video here showing what it does to tracers. So they include the tracers in the beginning of the simulation, and then they see how the internal tide breaking, all the overturns here, how they contribute to mix a lot of these tracer. And we're gonna see again in the beginning the tracers were way more concentrated here, but with time you can see that stuff mix away a lot. It's gonna spread way more, and that's because of the effect of turbulence by the internal tides. So I play it. Okay. And last, we're gonna talk about Lee waves. Lee waves are a kind of wave that happen when you have background flow interacting with topography. And these waves, these are standing waves. And what we have here, this is an example from the atmosphere. So you have all these ups and downs that happen in the lee of topography. And in the atmosphere specifically, this up and down movement, you can see clouds when you have an up because you bring all the moisture below the point of condensation, and you have all the clouds. You can see these in satellite images, which is really pretty. Sometimes you can see them out here too. And these waves, they're also gonna be important in the ocean, especially in the deep ocean when everything's really quiet. If you have any current interacting with topography, you're gonna generate these waves. So the Antarctic circumpolar current, for example, in the Southern Ocean is really important to generate Lee waves. And these waves, they propagate up, and as they're propagating up, they can propagate up into a background shear flow, and that variation in the media, the shear varying, can make these waves break through. So this is an example of you have a ridge, and then you generate the Lee waves, but as they're propagating up, they can break, generate these big overturns. And this is just temperature, but you can actually see turbulence also in acoustic measurements. This is backscatter, and you can see all this crazy thing happening here. This is the Lee wave that propagated and broke, increased shear and generated a lot of turbulence. Yeah, so this is all I have to talk for today. And just to summarize, we know that shear and strain are really important. These are really important variables that we use to study turbulence. Shear drives turbulence. Shear also steers tracers around and contributes to turbulent mixing. And strain, there's a strain rate that we can actually measure how much steering is going on, and there's the strain variance, which measures all the wiggles in the water column. We can use that to estimate turbulence. And then there are all these different processes that can drive either shear or some of them that only drive strain but don't drive shear. Yeah. You guys have any questions?
Can you go back to the definition of strain? And
Yeah.
say it again.
The strain rate or the strain variance? Both.
Both. I've always just been really confused. What is strain?
So first, the strain rate. The strain rate really just measures like how much local divergence, convergence, or shear is happening in the flow. And this is going to be a measurement of how much potential steering you're going to generate. So if you think about like into the like sum as a scale front, it's a region that's going to have a lot of, let's say you have an eddy here, another eddy here. This region is a region with a lot of convergence and a lot of also variation in current, a lot of lateral shear. This is going to be a region with strong strain, which means that the tracers, they're going to accumulate and stretch in these regions. So if you have some turbulence data, you compute strain and you see a bunch of like regions of high strain surrounding the Kelvin-Helmholtz billows. These are regions where you're going to have tracers stretch. And then the strain variance measures how much variance of the variance in deformation across a flow. So you can see that there are a bunch of wiggles here. They were perturbed because of turbulence, a bunch of wiggles here, but here it's all constant. So the strain variance is going to try to measure how much of those wiggles are there. And this is going to be useful for parameterizations and like get a sense of how much turbulence is happening without measuring turbulence directly.
So is strain a measurement of the potential for stretching and stirring, or is it a measurement kind of stirring itself?
The strain rate is kind of a measurement of how much stretching and steering is happening. Strain variance is a measure of how much deformation happened.
Okay.
So they're two different.
Maybe I'm thinking about this the wrong way, but so the strain rate can be like decomposed into like the normal part that's like convergence and divergence and then the shear part. So if you measure strain, how do you know how much of that is shear and therefore turbulence versus just like local vorticity or something? Is that,
Yeah.
am I thinking about this wrong or is that?
Yeah, if you have all the velocities and the velocity gradients, you can compute like each component of these and then the total, and then you can associate like, oh, this much was because of convergence, this much was because of shear. And then you can see how much each contribute to the total strain. But yeah, that's only if you have all gradients. Oh, so you can do this in a model, for example, but yeah.
So I was just wondering though, because you were mentioning like measuring the variance over the water column, or because and that seems weird to me because of the fact that you have like a mean value that could be very different, so it's like inherent that have high variance. Or do you measure it over areas that have turbulence only, for example? Like if there's, you know what I mean? Does that make sense?
Can you repeat it?
I'm saying that I don't imagine that the entire water column will have turbulence for that, and so therefore there's like this biasing term, taking a mean.
Yeah.
And then using variance for that. So that's why I was wondering if it's done only in areas that turbulence is involved or.
No, you can use throughout the whole water column, but let me go back to it. So this n square average is supposed to normalize everything. And then let me try to draw. I don't have. I can use what? Okay, so let's say you have a stratification profile that's kind of like this. Your n square fit is just going to be a smoothed version of this. Let's say just that. And then your n square minus n square fit is just going to get the little wiggles. And then you kind of average that to normalize, and then that's supposed to like isolate the little wiggles throughout the water column.
Okay.
Would you be offended if I offered another addition to that?
Yep.
I guess it happens.
Go good.
When B15 paper was using cargo floats. And so I think that the reason why she used this parabolic fit to a single profile is because in each location she only had a single profile. But in another scenario where you had, like, for example, a profiling mooring, and you could choose for your n squared fit to be like an average stratification profile. So you could do some combination of like either smoothing or time or spatial averaging in order to decide like how much of the wiggles on top of the profile are you interested in considering.
Gotcha, okay.
But yeah, it does kind of vary based on what observations you have.
Yeah, thank you.
Awesome, thank you.
I'm also interested in this fitting procedure, because it seems like, I think you're doing a quadratic fit to the whole water column, stratification through the whole water column. It seems like a parabola wouldn't do so well, because it's totally skewed towards the surface. And
Yeah,
it also, like, don't know.
yeah, that's a good point. Yeah, I think that kind of goes back to what Charlotte said. I don't really know the details of why they chose this, but I think what you really want is to find a way to smooth your profile and like isolate like what wiggles are supposed to be because of turbulence or not. And so, yeah, maybe quadratic fit will not always be the best thing, but maybe it was the easiest to do for arco profiles, the most generalized way.
She was also doing it with global data, so I'm sure that she put a lot of thought into like how do you come up with some sort of a fitting algorithm that is not biased in any way?
Yeah.
I have one more question. I think you mentioned this then, but the near inertial frequency is regional.
Yeah, because the near inertial frequency is F, and F varies with latitude. So at each latitude, you have a different period for your near inertial waves. Yeah.
Oh, cool.
Usually like at 29 degrees north is like about a day.
Okay, okay. Thank you.
There's a question in the chat as well. Nero asks, internal tides generate mixing, and can it also increase water temperature?
Yeah, internal tides can increase, can generate mixing. It can generate overturns, or it can radiate higher modes and then increase shear and break. And then if it's going to increase water temperature or not, it depends on what's the background temperature profile. The mixing can either cool sea surface water if you have warm water on top and cold water below. But if you have a situation where you have warm water below and cold water above, which sometimes happens in salinity dominated oceans, then it can warm the sea surface. Yeah, it's all gonna depend on the gradient.
And you had a comment as well about how to do the distinction between stream.
Oh yeah, so yeah, the Ukubo bias. See, yeah, thanks, Caique. That's true.
Any other questions? We can probably break for lunch. Yeah, so we'll come meet back again in about an hour. We'll move into Helen's lecture, kind of talking about different parameters of turbulence. So for people who are, well, we have picnic tables here. That's kind of where most of us normally have lunch. You're welcome to join us at the picnic table. If you need a break, you go for a walk or anything, feel free. Okay. And yeah, and like I mentioned, thank you. Yeah, so we're not in the dock. But yeah, like I mentioned, there's microwaves and fridges, and feel free to grab snacks. So if you want to warm up lunch, and there's also a cafe walk down the staircase, if you want help, I can show you how to get there, but there's some cafes where not if anybody wants to.
Thank you.
Yeah.